Okay, so hi, welcome to all. And today we're gonna talk about transformers, which is a neural network architecture that has been on rise in recent years. And well, we're going to introduce it from zero, so everyone can understand. We are going to give context on why it appeared and how it works. So we will start talking about a bit about NLP, what we want to solve, like linguistic problems with computers, because we want our digital systems to be intelligent. We want our voice assistants to understand us. We want to ask questions, extract information from the web and from other systems, and be able to retrieve that answers quickly. And we also want, like the other example, to distinguish misinformation from real information. And that are all tasks that require systems, intelligent systems that understand how language works. So here we have a problem. How can we represent language? Because in a computer, it is just a sequence of characters, like, for example, Unicode characters that don't have a meaning by its own. I mean, hello could be like 26, 37, 50, 60. That doesn't tell us anything about the meaning of hello. So we have to find an intelligent way to represent the information in a way that makes sense to the meaning. So the basic units for language are words. We are going to take words as the basic unit. The general approach that most information systems have gone along to represent language has been to create numerical vectors that represent words. This can be done in a lot of ways, and the intuition behind that reasoning is that maybe something that we can borrow from componential analysis, like in the figure in the right. You can see that maybe we could represent cat as some features like being feline, not being really human, like a low numerical score on human, not being royalty, but it is a living being. So if we have a lot of features like that, by a lot I mean a lot, like hundreds of features, we could encode the whole meaning. This is like the intuition behind. We will see that current systems will do this in a data-driven fashion. We won't tell the system which features it has to score, but the system will automatically learn the features that it thinks works the best. But we won't know exactly what is the meaning of each feature. But this is like an intuition. I like to say also that this is not like the only approach. We have other approaches to meaning, like compositionally, that Pablo is trying to work on. But there could be a lot of ways to represent meaning, and we are not sure. We don't know which one is the correct. But the vectorial approach is one approach that works well in a data-driven fashion. It scales well with data. So we are going to make a quick recap on history of NLP, very quick. The first model, well, we can model language just as predict next word, giving a sentence, which will be the next word. And this can be done in a statistical fashion, like we see in the right, like we have the bigrams, trigrams examples that we just collect on a corpus, which are the words most probable, which are the pairs of words most probable, the three tuples of words most probable, and with that, we can somehow predict the next word based on probability. This was the first attempt. And below you have a representation of what I told you. If we have a vector representation of meaning, like we introduced in the previous slide, we could do like some reasoning with the meaning. We could apply some maybe vectorial operations to meaning based on the dimensions we have on that vectors. This was the first attempts. You will notice that the progress is the marks are every 10 years. Now this has been accelerating in recent years. We have gotten like better vectorial spaces. From now on, we will call these embeddings. The vectors that represent words are called embeddings. And in the last 10 years, we see that it has gotten an exponential growth in research. And at first, it was just maybe a few neural networks, maybe some intelligent representation of words with vectors in an intelligent way so we can train it with a lot of data. And in 2017, transformers appeared and made a giant leap forward. So a question could be, why using deep learning? Now it's some fashion, but it has some pros and some cons. We can scale the model with a lot of data. It's also, we know from vision and from other fields that it generates really natural language in this case, or images. We don't need to parameterize language in the sense that we don't need to focus on syntactic features, on semantic features. We just let the model learn. But it also has really big cons. We don't know how it works. It is not explainable. It is a black box. It is not reliable neither. We are not assured that the model will perform well in a given situation. And also, there is not a trivial conversion between language and something that a neural network can process, like numbers, or what that is floating numbers is what a neural network is best at. So it is not a trivial choice like we see today that 90% of progress in NLP is done in deep learning, but it may be worth trying other approaches. What is the neural network, the deep learning approach? Well, we just have the feed-forward neural network that is like for us the holy grail, the thing that solves all the problems, and we just throw them the problem and we hope that it will solve for us the problem. But there is a few problems. As I said, we have to convert text to numerical vectors. Also, we must note that neural networks don't work well with inputs that can vary on length. So we have to find a way to encode sentences in a fixed length fashion. And also, well, it may be implicit, but the order of the words in the sentence might be a problem also. So the first attempts were using a recurrent neural network, these ones. This solves the variable length problem. We cannot fit a large sentence. I mean, for example, 200 vectors. If we train our neural network with 200 vectors, 200 words, we cannot then fit our neural network with 300. And this is very limiting. So we must find a way to be flexible on the sequence length. And RNNs do this in a recursive manner. We just input one word at the neural network. And the principle that works behind the neural network is that you input a word to the neural network, it processes the word, and it keeps an state. And then you input the next word, and it keeps an state, and you input the next word again. So we can see how for each word that is input to the neural network, it keeps an state that allows the neural network to remember the meaning of the sentence. This has problems. I mean, after the recurrent neural network, there was improvements like the LSTM here that focuses on remembering better. Another improvement, but this has problems. For one, when we have a really long sentence, it is very difficult that the information from the first words makes it to the end of the sentence, because the information has to travel all these bits, if you want to call it that way. And if you have 200, it is unlikely that the information from the first words will make it to the end. And also, if we want to do a sequence-to-sequence task, for example, translation, we want to encode an sentence in English and get the sentence in French. We have a problem. We encode the information like in the bottom, and then we have to have here all the information from the French sentence, from the English sentence in this case, condensed in that point. In that point, we have read the whole English sentence, and we need to start generating the French. So all the information from the English sentence must be in that state. That is a bottleneck, because the sentence might be very long or may have a lot of detail in the meaning, and that doesn't allow us to translate complex sentences. So the researchers in the early 2010s asked, how can we solve this problem with RNNs that are our best model now, but they have this limiting power, these limiting problems? Well, they came with a solution that has been really powerful in NLP, but also outside NLP. And it is called attention. Attention basically means that we bypass this problem of the bottleneck in the latest state of the RNN, and we allow the generation phase of a sequence-to-sequence model to attend every state in the encoding phase. So, for example, when we are here translating from English to Italian, I think it is Italian, when we are generating the word cellulare, I hope I got it pronounced right, the decoder, the generation phase, can attend to all the words in the English encoded sentence through a mechanism that compares the hidden state that we are using to generate the new word. It compares this, which is a numerical vector. We compare this to all of the individual encodings of the previous sentence. We are going to see this in detail, don't worry, in the next slide. You have to get the idea that attention, what it does is take a variable length sentence or sequence and focus on the most important parts. In this case, from cell membrane, when we are trying to translate cellulare, it will focus on membrane, on cell. And that's a really powerful mechanism. Then they saw that this worked really well, but it was really complex because we have the RNN, maybe the improvements on top of the RNN, like the LSTM, and then on top of all of that, we have the attention mechanism. So the natural question is, if attention gives us access to any encoder state, why do we need RNNs in the first place? So the big move was to remove the RNNs and keep the attention. Let's get just a bit of a glimpse into the workings of attention. We are translating again now from French to English. We want to start translating. So we have the embedding of the start of the sequence. One of the features present in the vectors may be that a word is in the start of the sequence or a word is in the end of the sequence. That may be one of the features of the vectors. Maybe this one. We don't know. The thing is, if we compare this vector here with all of the vectors in the codification of the of the French sentence, we just compare and we get a score here. To which word from the English sentence must we pay attention to start translating? Well, if we are human, we know it should be to il, to the first one. So with that, we now can start the translation having in mind that this is the important word to translate now in this time step. And with that, we can start the generation. For the next time step, we know that the train system knows that the attention must go to the entité. And this is how it works in a higher level. So transformer is just, well, and this is also a very powerful mechanism, like in this figure, to know what the model is trying to do. It provides us with some explainability of what is the model doing. We can know which tokens, which words is the model attending. So the transformer is basically taking that powerful mechanism and detaching it from the RNNs. RNNs have also another problem. Apart from the bottleneck and what we just solved with attention, they have the problem that they are inherently sequential. For computing the third word, we must have compute the second and the first, because the representation of the third word depends directly on the representation of the second word. That is not good for computing, because we cannot parallelize that. And we want to speed up things in GPUs and training a lot of data. So removing the RNN allows us to train in a parallel way. So we feed the words to the model in parallel, and we get a representation for each word. Transformer uses attention to incorporate meaning from other words to the current word. For example, if we are encoding the word je in français, then in the attention mechanism, we are going to incorporate the information needed from other words to the embedding of that word. And that is done without having a recurring structure like in the RNNs. And we also have another problem. How can we know now which word is first and which word is at the end of the sequence? We can tell because we are processing them all at one time, all in parallel. So the solution from the transformer creators is to bring in some signal, some vector that is summed up with the meaning, with the embeddings, and that tells the system the position of the word in the sentence. And the transformer is just this, in a higher level. Take this powerful idea of attention, make it work in parallel with, and at first it might seem like really complicated, but we will see it's not. It incorporates a stack of this mechanism that we just talked about, allows us to mix the features of different words. So we can contextualize the words. Like we can, in a sentence that we have a word like, for example, fine. We cannot know if fine is from I am fine or from you have a fine. It's a very different meaning. So the attention mechanism from taking features, if the sentence is the police find me, from police, it can know that fine is in the sense of a bad sense. But attention is the mechanism that allows us to make the vectorial representation contextual. And after that, we have a feed-forward neural network. The feed-forward that we just talked about before is a powerful mechanism that will allow the system, after that contextualization, to work towards the the training goal. So if the training goal is to translate, the feed forward taking the information from the attention mechanism allows us to output the desired translated sentence. So the transformer has some key things. We just talked about attention and the feed-forward neural network after the attention that makes the transformation and the complex information processing. It also is when we call it is a deep neural architecture because it is really deep in the sense that all of these blocks, this one and this one, they are stacked. There is not just one. There is like one, and after that one, another, and another. For example, 10 of them. Also, this mechanism of attention is not only one. It is like 10 or 12 is the standard. So one attention mechanism can pay attention to the subject, for example, to contextualize words and to know, to resolve problems like when you say it or he, who is that word referring to? It's referring to another word in the sentence. So one attention head can pay attention to that. Another attention head can pay attention to syntactic dependencies. Another attention head can pay attention to gender. Another attention head can pay attention to whatever it is necessary to solve the task. So we have a stack of attention heads working in parallel, each one attending different features, and after that we have a feed-forward that gets the info from all the attention heads, and that we repeat that process n times. We will see everything of this in detail. Now I want to take a step down and analyzing in detail what is happening here. Because we feed something to the transformer, but sometimes we don't know exactly what it's doing with the data. The process is this one. You have, at first, the text. You need to tokenize that into words or whatever the units that the system processes. It might be subwords. Like we might split the words into halves or whatever. All of this is data driven. The system decides how to do all of these steps. After that, we convert that tokenized words to unique numbers. That unique numbers get converted in the embedding layer into vectors, the vectors we just talked about. And that vectors with a positional encoding for what we just said, for knowing where in the sentence that vector is, it is at the start, it is at the end. With that positional encoding, it starts to flow through the neural network. So keep this in mind because it's easy to mix. First, we tokenized, we give input IDs to the word. Each word that is now a number gets a vector representation, and that starts to flow in the transformer. So now let's look at the transformer itself. We must remember that now there are vectors. Each vector represents a word and has the position encode flowing through the system. And with these vectors, this is the overall architecture of the encoder. The encoder has the role of taking the original vector representation and make another representation of vectors that is like processed, like a representation that makes the task you want to solve easy. It might be one for translation. If you want to do a sentiment of analysis of sentiment, you might want another representation that focuses on whether each word is positive or negative and how do they interact. So the role of the encoder is to process each word in an intelligent manner and to contextualize each word so that every word has the meaning, all of the meaning of a word is encoded on its vector. It doesn't depend on the other words. And we do this through a stack of encoders, as we saw. And we have first the self-attention and then the feed-forward. And we repeat this process. For each word, self-attention takes the meaning from other words that it needs. As we saw, just for contextualization, if we want to know if fine is a fine or is to be fine, the vector of fine will take the appropriate meaning from the rest of the words that mark that context. And after that, we build that in a hierarchical manner. I will explain this. At first, in the first layer, we will extract like obvious context features. After the first layer, it will start making more abstract. It will start extracting more abstract meanings, like constructing on the previous ones. So you can, language is complex. So at first you will extract like simple meaning from the words, and then with that that you have extracted in next layers, you will take like meanings that are complex, that need a lot of processing. We will see this more in detail. We will now see how we can do positional encoding. It's not a trivial task. At first, we will say, oh, we can just add a 1 to the first vector, a 2 to the second vector, and an n to the last vector. Problem solved. What is the problem? Well, the problem is that if you add a 1 to the first vector and a 20 to the last vector, you will modify the meaning of the last vector substantially. Because if you are adding to all the vector like 6 or 20, you are modifying the absolute value of the vector in all the components by a lot. So that doesn't work. Well, we can add like a digital binary counter. And that can work because we are always adding like 1 or 0. And we say, this seems a good idea. But the bad news is that feed-forward networks work with continuous data. They don't work with discrete data. So we want to try to make it continuous. How can we do this? Well, as we see in the figure, sine and cosine waves can give us the approximation of a binary counting scheme through a continuous wave. And that's what is done. We just start, depending on the position, we add a sine wave or a cosine wave that tells the transformer where in the sentence is each word. And this works really well. Some other approach were tried in the original paper, but this one seems to work better because, well, of mathematical properties of sine and cosine, they are all linearly composable. So the thing is that a neural network that is a specialist in obtaining relations and especially linear relations can extract the order very well from this positional encoding. Now let's see how self-attention really works. We have here a sentence when you play the Game of Thrones, and we want to contextualize, for example, game. And we say, okay, the meaning of game in this sentence, it is the meaning of game itself, not contextualized, but also for giving context, we also need the word Thrones because we are not playing any game. We are playing Game of Thrones. So we will zoom the features from the Thrones vector to the game vector. And that will be the game vector contextualized. When we do this across all the words, we get an attention matrix that tells us for each word how important are the other words. with this matrix, we can do a direct multiplication. So if we have these scores, we multiply by the original vectors, and we get a contextualized vectors. We must note that doing this, here in the sum we are doing, we don't care how much vectors we have. We don't care if the sentence is 20 words or 30. We don't care. We just sum the vectors, averaging by the weights of the importance relative to the attention matrix. So this is a powerful mechanism to concentrate to put into the contextualized vector the meaning from all the words, no matter how much they are, how many they are. And how can we do that? Well, we can inspire in a mechanism from information retrieval that we know as query key value. We have the word it, for example, and we don't know it to what is referring in the sentence. So we compare the representation, and we know that after comparing, the comparison says, well, it is 50% similar to the robot and 30% similar to the A. Well, then we have the key, we have the query, and then we get the value of that. This is just like an analogy to understand how it can work. We compare different vectors. With that comparison, we get scores to how similar they are, how relevant they are, and with that scores, we make an average sum that tells us the contextual vector. This is done in a matricial fashion. We just, from the original word, we have linear layers that are trained to derive the key and the query, and also to derive the value. And we can see an intuition of how this works from the cosine. We see that the cosine of two vectors, when they are really close, the cosine approaches 1. And when they are 90 degrees apart, the cosine approaches 0. So a measure of similarity between vectors is to do a cosine, a dot product, and divide by a scaling factor. This is just self-attention. Just do that. Compare each words using the cosine procedure, seeing how close the vectors are, divide by to normalize, and with the softmax function, we can have, from the value of similarity, we can have a percentage. So we can build something like this. Like we have a score for each word. This is given by the softmax. So in the end, it's just this, comparing each word to another, getting scores, and using that scores, just multiplying by the factors in a weight average fashion. We said that attention was a multi-headed beast. We know that that one head can attend one type of thing, like a syntactic feature. One head might be interesting for each word attend its syntactic parent, and another head can be specialized in attending the gender or another aspect that the transformer might decide in this training. And attention, at the end, it was a really great idea because it was cheap in terms of we didn't need the RNNs, sequential, very costly computation. It performs really well in translation. It works really, really well. It gives us, as I said before, a fixed representation of a variable length sentence, and it allows for the feed-forward network in the next stage to check the features that the feed-forward network is interested. And the feed-forward network doesn't have to do the work of extracting the features that it needs and then processing them. Feed-forward can just attend the selected features that the attention has already put in each word. After that, if we look at the figure of the transformer, we have our input vectors, we have our positional encoding, we have the attention that we just explained, and after that we have the neural network. Well, all neural networks need normalization. We know from that from gradient propagation, the way we train neural networks, that if the data is not normalized, we can have really bad problems. So we need to normalize. Transformer architectures do this in every layer, every attention, every step in the pipeline is normalized afterwards. We also have residual connections that have shown to be a really powerful mechanism in vision. And they also help with training because information may vanish through all the layers. So with residual connections, we can skip and retain the information. And from the people here that is not for computer science, a feed-forward network that is very fancy, represented as this, at the end is just a matrix multiplication. We can do this efficiently. It's just, as you can see here in the expression, it's just representing some function, some matrix, multiplying by a vector, summing the bias, and applying a nonlinear function afterwards. But it is not a complicated thing from a computing perspective. We must remember in that this is done for each token. We cannot lose perspective and think this is computing the sentence. We are doing everything for each token, for each word. And the only way to combine meaning from words is attention. The rest of the pipeline is done for each word in separate. So this is the encoder. We just got our initial vectors, embeddings, and we have processed the embeddings through a stack of repeating encoders that first pay attention, then feed-forward network for each word. This is all it does. And now we see the decoder. The decoder is the part that if the encoder takes for example, the sentence in English, encodes a powerful representation of the sentence in English, then the decoder will start generating the sequence in French. We must note that we only need to encode one time. We encode the sentence in English one time, and then the decoder for generating every word in French will reuse the same representation. So we can see here in the animation how it works. It gets the encoded representation, and in each time step, the decoder starts generating the translated words. And the powerful thing here is that in inference time, when we want to do a real translation, we do this. The transformer, the decoder, just starts generating in a sequential, generates one word, then another, based on what he has already generated. But we can train this in parallel. When we train, we don't need to first output the first word, then the second. No, we can put all the sentence at once and train in parallel. We will see this in a minute. So during inference, we have this figure that we see. We have the encoder output. We just calculate the encoded representation once, and then the encoded representation of the original sentence is fed to all the stages of the decoder. We don't need to calculate it anymore. And from the first pass of the decoder, it generates one word. Then it generates another word. Then another word. It is recursive, as the RNNs. But it is just when we want to do inference in real world. When we train, this is what it happens when it trains. Because of self-attention, we don't need to wait for the previous word to be processed to process the next one. We can start working with a student without having processed I. Because we know when we are training, we know how we will translate the sentence. We know the sentence in French is Je suis étudiant, and the sentence in English is I am a student. So we can assume that the model has already gotten the previous words well, these ones, and we can train for a student at the same time that we train for I. This is an innovative thing of transformers that has allowed to be really fast and to train enormous size of data. Because if we have a parallel machine that is very fast, we can apply it to enormous corpuses of data. And this is one of the major innovations that has led to the rise of transformers. We will see now how the pink box works in detail, the decoder. Well, at first, just note that it is very similar to the encoder. The encoder, from an initial representation, encoded a powerful representation. Now we do something similar. We encode a representation that allows us to generate the next word. So in that sense, it's similar. There is just two changes. We see here self-attention, that the arrows are only forward. And we see also that we have a new block here, named cross-attention, apart from the self-attention. We will start with the mass self-attention that is here, these arrows. The thing is, if we are training in parallel, and if we are training for, in the example before, a student at the same time as in I, well, we cannot let, when we are translating I, we cannot let the model see that the next word will be am, because that will be cheating. So what we need to do is, through attention, we don't let the model observe the future. It's just that. It is a simple change. We can represent it in a lot of ways, like here in this figure is very illustrative. And in a practical manner, it's just the attention matrix that we saw before. We just apply here zeros. So when it does the weighted average of all the words in the sentence, the words that are in the future cannot be attended. Simply, it cannot see it. Now we will see cross-attention. Cross-attention is what allows the decoder to generate new words based on what the encoder has represented. So when we are translating, we want the transformer to be able, when it's translating, je suis étudiant, I am, when it is outputting the word am, we want the transformer to focus on je suis, because it is the word it is translating. So cross-attention is an attention mechanism that allows the decoder to focus in the appropriate part of the encoded representation. So at each time step, the cross-attention takes the encoder output, makes attention, so it gets a vector of the most relevant features, and outputs that to be summed up with the current decoder state. And it is just that. Here, I am not representing all of the rest of the residual connections that skip layers, but the residual connection that skips the cross-attention is really important because it is the only thing that keeps the previous vector from flowing through the architecture. Because cross-attention takes the encoder vectors, and I will just remove this. Cross-attention takes the encoder vectors, and that's what it outputs. The encoder representation of what is going now to process. So if we want to keep the previous representation from the decoder, we must do it through the residual connection. Okay, so this is just the decoder. We can go back and we see that it is like encoder, but the only difference is that the representation in the end goes to generate the next word, and it has some changes, so it doesn't see the future, and also so it takes into account the encoder to generate the translated sentence. And that's what we have here. It is really similar to the encoder, and this is all from transformers. It is all we have to understand from an architectural point of view. Now we have a lot of ethics and application related topics that we must discuss, but from an architectural point of view, this is the encoder, the transformer. We just like to take a glance at this part. From the decoder representation, we must generate the next word. How can we do this? Well, if we have a vocabulary of 5,000 words, it will be more, but we just map from the output vector to 1,000 to 5,000, or how many we have outputs. After that, we apply a softmax, so we have probabilities, and we select the word with the highest probability. It is a simple thing. And we must know that generating new text is not trivial, because, well, we can say we just take the next word that has more probability. In this case, it starts generating, it says there, and then the next one, the nice, and the next one is woman. But maybe if we explore other paths, we can see that this word here has less probability, but then after that, the next has a higher probability. So this is also a search problem that is a classical problem of artificial intelligence and computing in general. And this conditions a lot also the quality of the generation. It's not a trivial problem. Okay, so here we have an architecture recap. This is all the transformer. There is no more secrets in the technical architecture. We just have the encoder that takes the text, makes embeddings, vectors from each word, for each word, puts attention so it can contextualize each word, passes that through a feed-forward network that processes the features in a layer after layer in a stack of encoders. We get with that a good representation for the task we want to solve, and then we start generating with the decoder. The decoder does something similar, encodes what it has already generated in a contextual manner. Then it incorporates the information from the encoder. Then it passes that through a neural network, repeats this in a stack of layers, and after that we generate the next word, and the process starts again. So why does it work really? Why is this architecture beating the state of the art in so many tasks? Well, there is a paper really famous. Well, there is some of them, but in particular, a prime invertology. It's one I really like that tries to explain why this is working. At first, if this works in some kind of it must be because the hypothesis that we can decompose meaning of words into components of vectors must work at first. If not, the architecture would not work. And the transformers divide this in a lot of features for each word and make operation on that features. So at first, in the first layers, we might have like trivial features like gender, like basic meaning. And at higher level, we have complex meaning features like, is it positive? Is it negative? Is it human related? Things that require a lot of abstraction and a lot of complex analysis of the sentence. So if transformers work, this analysis must be at least partially well done or partially possible. Language must be possible to be expressed in that way. We don't know also if this is how humans work with language, but we might do something similar in our heads. We combine meaning. We reason with the concepts behind. That it's something, spoiler, that transformers don't do. Transformers are just talking parrots. They take words, they combine it, but they cannot reason apart from that. And also something we have to think here is that maybe it is not the best model for language, but what happens if you have a really good model that it cannot learn from a lot of data because it doesn't scale well, it doesn't take advantage of modern compute capabilities and lots of data. But if this model is not that good, but it can scale with data and learn from enormous corpus of data, well, then maybe even not the better model may do it better in the end because it can learn effectively from a lot of data. And one of the problems of transformers is explainability. In general, feed-forward networks are complete black boxes. We cannot see through them. Attention provides some interpretably. We can see in which, at least in the first layers, we can see in which words is the transformer focusing to do the processing of the sentence. And this allows for some interpretably and for some explainably. Other techniques include probing. Probing is in the stack of layers. We just put a neural network in the between of two layers, and in that neural network, we just try to predict gender or to predict position, and we can see from that probing strategy what is the transformer doing in that layer. Also, a very interesting trend in transformers is pre-training. It's very costly. Training a big transformer can be as long as a month in powerful GPUs from scratch. So what is done is it was observed that you train a model for translation, then you want to train it for summarization or reverse, like in the slide, and the training time is a lot less. You train it first for a task, and then adapting that transformer to another task because it already has all the language processing pipeline that can be adapted, the weights can be adapted. It is like a lot of less time. This also, from an optimization perspective, when we are doing a parameter optimization, pre-training can be seen as leaving the highest, approaching the global minimum of the optimization, but we have to take into account that this is optimization in maybe hundreds of millions of parameters. So, well, it is a very powerful trend that allows us to take pre-trained models and quickly adapt them to new tasks and to tasks that we may not have a lot of data. And this trend of pre-training models has led to a workflow in natural language process that when we have a problem, we just look through the available models and we ask what of the bigger models, pre-trained big models that we have fits better for our task. And there is a lot of them. We will see now some of the most famous, but there is a lot of them. The first one, GPT, invented by OpenAI, the company of Elon Musk and now Microsoft. It is just a decoder, no encoder part. It's just a parrot. It talks and talks, but it cannot encode information for a task. So how can we teach it to do something similar, to do something useful, if we cannot put the encoder? We remove the encoder, and we get We get only the decoder. Well, if we say, for example, instead of putting in the encoder the English sentence and then expecting the French from the decoder, we take the decoder and we say, English, 2 points. My name is Manuel. French, 2 points. Now start generating. So the model, being only a decoder, can learn how to translate from English to French. This is less powerful in principle, but the training is more simple, so it can learn from more data, and it was like the first attempt they made from books specifically, because books have long-term dependencies that you don't see on tweets and other kinds of data from the web. So it is less powerful, but on the other hand, it is more simple. The next one, and the revolution, was BERT from Google. And this was the opposite. This was just the encoder part, a stack of encoders. The novelty here comes also from the way they pre-train the system. Instead of completing text like the previous one that was just give it a text and what is the next word and the next word and the next word, and the model just learned to do that and then fine tune on task. Now in BERT, it presses the wall task and they mask a word in the middle, and they ask the model, which one is that word that we have masked? What this effect has in the model, it is that it doesn't learn only the next word, the next. It learns the language model from a bidirectional perspective. It takes information from the left and from the right. It understands language and sentences as a whole. It doesn't depend on the linear sequential nature of the decoder. And this was really useful for things like analysis of sentiment or predicting spam or whatever task that requires a global understanding of the sentence. Because of this way of pre-training, this was a major leap forward, and it gained a very deep understanding of text. We can see the scale of the model. It has begun to raise. Now we have 12 layers, 12 attention head for each layer, 12 attention head, not in total. It is 12 by 12. And in total, it was like the base version, 100 million parameters. The large version was 300 million parameters. This is enormous. We can see here the training time in 8 very powerful GPUs, the initial training time, not the fine-tuning training time. The initial training time, 21 days from that. It is really, really big. It makes the model, and this kind of models, it makes it unaffordable for small companies or research centers. Only the big players like Google, Facebook can pay for this computing power. The next evolution of the previous one was GPT-2. This is the same architecture. The only thing is that they increased the size. We saw in the previous slide, 300 was a lot. Well, now you have 700, and now you have 1.5 billion parameters. And well, they just the thing they did is they trained in a lot of tasks, not only on completing text. And this was really powerful for generating text, but this was just a scale-up version. Here we have, it might be interesting to see when we say 100 million parameters, where are the parameters? Just for getting a glimpse. Well, we can see that a good part of the parameters are in the are in the embeddings part. The layer that converts words to vectors. Then we have the 12 layers of the transformer. In this case, it is GPT, so it is a decoder, and we can see that most of the parameters are in the neural network, and around a third, more or less a third, are in the attention mechanism, because attention, as we saw, has some. It is not a neural network, but has learnable parameters to get from a word the key and the query representation. That is learnable, and those are those parameters. Now the next evolution was GPT-3. This was like a news bomb, and everyone was talking about it. But in the end, it was just increasing the size. They just increased the size to something that only 1 or 2 companies in the world can achieve, because it is estimated. Well, I have it after later, but it's estimated that it costed like 5 million to train it. So nobody can really do this. And well, they said no, it's just not. It of course performs well on tasks. It better may. And if we put this amount of training and it doesn't perform well, what are we doing? But what they say is, it doesn't only perform well, but it starts reasoning and it starts to resolve to be able to accomplish tasks that it was not trained for. So, for example, translate English to French, it was not trained to translate English to French. But when it was given that prompt, it could translate. So that was the point of the paper. But it also had a lot of problems. For example, when we train with this amount of data, we cannot select what data are we training with. They just go to the web and scrape whatever they can. If they find a blog post, that goes for the training, because they need all the data they can retrieve. So it gets a lot of biases from humans in the end, because they are all biases that get into the model. But they say that you must have caution when you apply this to a real world system, because when they complete when it completes sentences that start with use with black or with woman, it may do things that we don't want to be in our production systems. And this is a rising concern in this kind of systems that can catch all kinds of biases from the data, but we don't really know how they will perform after that. The next one was T5. This was a model by Google, and here the novelty is that they don't just throw more parameters at the transformer. They do a really well, a really scientific study of each part of ablation studies. Why do we need 10 layers here and not 12? How we pre-train? Is this the best way of pre-training? Is this the best way of fine-tuning? So after all of that study, it was a very useful model. And it is the default choice now if you want to do a language task that you have new, that you have a small amount of data, you're going to get this model and fine-tune it for the downstream task, because it works really well. It is a really balanced model for doing all kinds of tasks, and it is a complete transformer. It's not like the previous ones, an encoder only or a decoder only. It is a complete transformer, and the point of the paper also was to mention that all the tasks can be expressed in a text-to-text fashion. We can say translate English to German, and it translates in a text-to-text. But also tasks like comparing, classifying, giving a score, they can be achieved with a text-to-text transformer. This was previously done through an encoder-only architecture like BERT, if we want to make a spam classifier, for example. But they showed that a complete transformer with encoder and decoder was also the best choice for this kind of tasks. If anyone here wants to try out these systems, I want to show you this. The Hugging Face ecosystem is just a website. It's the publisher of the transformers package in Python, and it makes it really simple to use this kind of models. They have all the models pre-trained. You just have to write like a few lines of code, and they are free, available, open source. They have guides and documentation that are really well written. So everyone that wants to try it, just go to Hugging Face because it is really nice. They also have applications like not only code-related resources, they also have web applications that that allow to play in the web with this kind of models. And now we are getting into the problems and criticisms of transformers. First, we have in that corner the rise of parameters. This is considered by a lot of people unreasonable because we are getting in a scaling that just a few can continue because we cannot, no one can really afford to do that scale of transformers. We also have to take into account environmental concerns, like for example, GPT training is estimated to require that amount of electricity and carbon emissions. And after all, we don't really know if scaling the size of transformers is yielding more powerful and intelligent systems, or they are just overfitting over language. I mean, are just talking parrots in the sense that they just output the most probable thing in a linguistic manner, but what they want to achieve with that sizes is more intelligent systems. We are not sure that that this is happening, and there is a lot of criticism to these models for that reason. Also, when training at these sizes, as we said before, we just scrape from the web all the data and text we can, and we cannot control the biases. We might be scrapping a racist or a website or whatever, and we can't control what are we training with. Current research of transformers in the architecture, they just try to find more efficient ways of doing all of this computation, of removing tokenization, making models capable of different tasks without fine-tuning, multitask learning. And now we are going to see a few examples of transformers applied to tasks that are not directly, at least, text related. So, for example, there is vision transformers. Vision transformers is just taking the concept of a transformer and trying to apply it to an image. The problem here is that image is not a sequence, at least in theory. But we can do, as we say there, a projection of the patches of an image in a way that it is a linear sequence, and then pass that through a transformer. It may seem not really natural, and sure there will be a more natural way of doing this, but they are beating state of the art in image classification ImageNet. And why are they? Why do they think that this is happening? Because traditional image models usually attend images in a cone wave. They extract like the little details in a photo. Then from that details, the convolution forms like shapes and objects, individual objects. Then from that, we abstract like complex objects. But it is from a locality perspective. Local details go to local objects, go to near objects, more general objects. But transformers, thanks to attention, they can attend simultaneously to one side of the image and to the opposite corner. So they can reason and they can make a classification taking into account not only local details aggregated in a cone shape. They can also think at the same time if they are processing this image in this corner and in this corner. This is more general, and this works for some cases that previous approaches were not working. So that is what is thought to be the reason of transformers beating state-of-the-art in ImageNet. There we have a wonderful model called Dali, in tribute to the famous painter, that is really awesome. You can see that you give to the model in the right, you give to the model a textual description of an image, and the model can generate artificial images that at first this could be done by a human. I couldn't tell if this was made by an AI system, and it is really, it is not something that it will see in the training data. It is really generating a new image. And this model is also powered by transformers. How they do it is they have a classical autoencoder that tries to compress an image to an intermediate representation, and then regenerate the image. Well, they do a lot of research about this process to generate a powerful representation here at the middle. And then they apply GPT-3, the transformer. They give it the description of the photo they want, and then train the model to generate the intermediate image representation for the image that we are trying to generate. So the transformer learns to generate this representation that will decode the image, and the results are astonishing. But like with all of these models, this is huge, and this was trained by OpenAI, the same company as GPT-3. And finally, another interesting application that I know some of you here also are pursuing is to understand speech. Speech is traditionally processed through a computing system, extracting features like the pitch, well, that type of things that I don't know about. And then after that, that is converted to words and to phonemes. I don't know how it works. But the thing is that with this kind of systems, they have reached a system that with image analysis techniques like convolutional neural networks, they analyze the voice pattern. With that voice pattern, they extract features that they fit into a transformer, like if it were words or tokens or letters. And the good thing about this system is that, as you can see, most of the phonetic and the representations for the voice can be shared across languages. So we can take a model like this, and with very few training data, because we have a low resource language, like it might be the case of Galician, but even with fewer resources like African languages that have only a few hours of recorded speech, we can, with this system, thanks to this transfer learning procedure, we can get like a state-of-the-art performance very close to the big languages. And this was a major leap forward for this kind of models. So this was it. So if you have any question, also in the Teams. So don't be shy. Any question, especially from the linguistic part. Yes. No, I meant from the linguistic or the contextual ethics part. Something about the Chinese model. Yeah. Really huge, more than 1 trillion parameters. Yeah, but what happens is that there is some models that are bigger than the GPT-3, but they are also sparse in the sense that they process a part of the pipeline. They have a conditional. So if the representation takes like this way or another way, they apply this network or this network. So in overall, the network is really huge, but it is not a complete sequence-to-sequence pipeline with a lot of parameters. So it's like cheating on the number of parameters, because now also in the news and in the hype and what it sells now is to say, oh, we have the biggest parameter with 3 trillion parameters. But in the end, the ones that work well are the dense ones. That is what there is also one from Google, the Switch C, that is also in this thing in this way, and also has like, I think it's 10 trillion parameters, something like that. But it's like a collection of neural networks aggregated, not a complete one. Sí. Sí, sí, sí.
Yeah, so this does come from like a linguistic model. So can you tell us a bit about like model evaluation?
What?
Model evaluation. How can we evaluate this?
Well, there is some benchmarks that are standard. So we have, for example, the glue benchmark that takes like a small data set. They allow you to fine tune in a part of the data set. And after that, they have a test data set that you try your model on. And with that, they make a leaderboard in the same way that is done for ImageNet, for example, in Vision. The thing is that every time you make from a measure a competitive kind of thing, the measure gets perverted and it becomes the objective. So you might not be able to pre-train directly on that dataset, but you can pre-train on something very similar. So you end up cheating the evaluation. So it is not easy to evaluate these kind of systems, but there are a lot of initiatives to try to standardize that evaluation. So, for example, in the glue benchmark, they try to evaluate not only like completing or doing some tasks, but also question answering, because these models can have word knowledge embedded in the architecture. They can answer like general word questions like how many oceans there is on Earth, that type of things. But there is also reasoning questions that the models have to answer. And in that reasoning kind of evaluation, we have in the recent months, they have achieved like a high score. But when you take the model and put it in inference to reason about everything else that is not in the test, you see that it doesn't perform that well like it shows in the leaderboard. These models, we saw here in GPT-3 that it can do like really well. I didn't put it here in the slide, but you can start for example, a fiction story with an invented animal, and it will continue the fiction story with an invented animal. They are very good at that type of things. But reasoning, like giving a premise and asking the model to make a logic reasoning, they are not really good at that. That's why we say that they are like talking parrots, because they do language very well, but they cannot reason. And that type of evaluation are kind of perverted. So they are now researching of new ways of trying to pursue that. With?
Well, I just wanted the model. As you explained in the video, having language and text, but about the hardcore. And I just wanted to make a comment about because you explained, for instance, that there are millions of parameters. It takes perhaps several days to be, and in some the problem that you have to react very quickly. And for instance, COVID is now a very good example of this. And now words and terms that some months ago they didn't exist. So if you work with a model that was built some months ago or even ago, perhaps you are not doing a good job on the task that you are trying to do. And on the other hand, even if you are Google or Amazon or whatever, you can afford the build of your model every short period of time. But still, this, as you mentioned here, this takes a lot of time regarding the use of energy. So there is here some sort of trade-off. And for some applications where you essentially have some kind of, let's say, static use of language, then perhaps you can work with a model that was built several months ago, and that's it. And the pre-trained version, or as explained, sort of fine-tuning. But in other cases where it's really important to react quickly,
Yeah. First, thank you for your appreciation. It was a pleasure also for me. And related to the question, well, first, we must note that this is a general problem in artificial intelligence. Well, not in artificial intelligence. This is a general problem in deep learning in particular, that when we see natural intelligence, we are doing like inference and training at the same time. We are learning and experiencing with the world at the same time. Neural networks cannot do that. And the solutions aren't really there. For once, you could train, like fine-tune every few months, but you don't really have, so there is two problems. You have to train, but you also have to get the data. It is not easy to get the updated data for that training. And really fine-tuning a system that is in production and that may cause any error, it is neither a solution, because the fine-tuning of these models can be really tricky and difficult. And maybe if you change a bit the data, it doesn't perform that well on the task that you're trying to do. So there is not easy solution. The only solution that I have seen is this GPT-3, where they say that when you have an enormous model, you can do things like this one, of putting a task that it has never seen or it has seen or very little in training, and giving an example in inference, it can learn how to solve that task in inference. You have your model trained, it has like some reasoning power, take this with a lot of quotes, but and this performs really well. For example, this was the first model to be able to do mathematical operations, and it can operate with new words and imaginary words. So in cases like COVID or changing vocabulary, it might be able to operate. But this model is not operational. I mean, this is a cool research done by OpenAI, but this is really slow. This is 200 million parameters. You cannot put this into production and expect this to work quickly, and it is not reasonable. So it is an open question that there is ongoing research for that, but the current answers are not good enough. Any more questions? I don't know if in Teams maybe. Can transformers, we have a question from Promettory. Can transformers be applied to tabular? Can transformers be applied to data classification or processing? Yeah, of course. We talk about language, but transformers can be applied to every kind of data that can be represented as sequence of vectors. I have put an example of vision transformers when you take an image and you represent an image as a sequence of vectors. You can do this with an electrocardiogram, with a signal from your heart. You can do this with music, with all kinds of data. So if you have tabular data, yeah, you can. There is also some models that do that type of things. Yeah, of course. All kind of data that can be encoded in a sequence of vectors is you can express it as transformer. In the word value matrix, why the values of in the principal diagonal are not 1 in all the cases? Yeah, let's answer that. Well, can I see? Okay, wait. Yeah, I have to, because I don't have now the slides, I have to put it again. So, okay. In the slides, as you can see, well, in the attention matrix, why not everything is a 1 in the diagonal? Good question. You can see here that when we want to contextualize game and we take the word game, if we put a 1 in the diagonal, that would mean that all the meaning from game came from the game word itself, and we don't want to do that. We want to express the meaning of game in relation to the rest of the words. So the logic thing is that most of the meaning comes from the game, but also because it is Game of Thrones, it comes from game, but also from Thrones. So it cannot be 1 in the diagonal because some of the meaning is from Thrones, and it has to sum up to 1 in the row. So when you do the average sum here, you get a 1. It is an average sum, so you just move the weight from game to Thrones, and it has to sum up afterwards to 1. So that's why it is not a 1 in the diagonal. I will see things here. It's more easy, so I can keep the slides. Okay. So, any other question? Yeah. 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 Well, the question for the teams is about the bias of the models when we fit larger amounts of data. How can we avoid that biases? There is not a clear answer. The thing is here that if we want to train really big models need really large amounts of data. You cannot train a lot of parameters without a lot of data. And if you want a lot of data, you cannot restrict to small controlled corpuses that you know they have not biases. But even then, we can see that even BERT, that these models like GPT-3 was trained in the web, like from all sources from the web, everything they could get. But even BERT was not trained in that fashion. BERT was trained from Wikipedia and book corpuses. That is a very restricted training procedure. This is because BERT is smaller than the other models. But in the slide you can see, I don't know what it was here. In the slide we can see that here we have an example of BERT giving examples of sexist examples of professions So there is not clear answer. We could make a system on top of that to try to localize this bias, but in general, in the industry, the general approach is to try to mark very well where are we applying these systems, not put it in the wild. Like if we want the system for a purpose in particular, just restrict the model to that purpose, so it cannot deviate from that and filter the output, so the undesirable outputs don't go further than that. But it is a difficult problem, yeah, of course. Any more questions? No? Okay, so thank you very much for attending this talk. I hope you got a nice understanding of transformers. If you have any further question, you can contact me, no problem, or ask me for the slides. So thank you very much.